let's look at the Sturm-Liouville problem, and we want to remind you of a theorem that is associated with this problem so that the important results associated with it are familiar and can be used by you. So the Sturm-Liouville differential equation is written here involving the functions p, q, and r. Remember that the first and second derivatives have been combined into this first expression here. Q is the second function, and r is the third function. Lambda is a parameter that appears in the equation, and this equation is defined over an interval 0 to 1 for x, the independent variable, interval called as I. And as we have noted before, if the problem is defined over a different larger interval or a smaller interval, one can rescale x so that it is defined over 0 to 1. And so under the assumption that these coefficients p, p dash, and q are continuous over this interval, and that this function r is a positive function, it's positive everywhere on this interval, and given these boundary conditions that a linear combination of y and its derivative at the location 0 at one end of the interval and at the other end of the interval with a different linear combination, or could be the same weights but with some constants b1, b2 and a1, a2 all equal to 0. So reminding you that the differential equation is homogeneous and the boundary conditions, both boundary conditions are homogeneous, gives us a homogeneous boundary value problem. And in general, such homogeneous boundary value problems cannot be solved. In the present case, they can be solved because they involve an arbitrary parameter lambda. And so viewing the parameter lambda as the eigenvalue, viewing this whole problem as an eigenvalue problem, we can look for conditions under which this eigenvalue problem can be solved. And there is a very important theorem associated with that, which we want to now describe. So the theorem says that there exists an infinite sequence of eigenvalues. We are calling the eigenvalues with a subscript j to label the eigenvalue sequence. There exists an infinite sequence of eigenvalues, lambda j's, and corresponding eigenfunctions, which we are also labeling with the subscript j, eigenfunctions phi j, such that following properties hold. And so we can order the eigenvalues according to increasing values. So lambda 1 is the smallest eigenvalue, lambda 2 is the next bigger eigenvalue, all the way up to lambda k and going on, bounded by infinity. So all eigenvalues can be ordered and they are less than infinity, such that as n in this sequence goes to infinity, the eigenvalue goes to infinity. So these eigenvalues approach infinity as we go to larger and larger index n. The second property associated with the eigenvalues is that the eigenvalues lambda j's are real and they are distinct. Real is obvious, meaning that they don't have any imaginary part. We have real valued numbers, lambda j. Distinct means that there cannot be any duplicates or triplicates of or higher copies of these eigenvalues. They are all simple eigenvalues. They have, if we think about eigenvalue problem, they are never repeated. They are simple. All right. And now we want to describe some more properties. So the other important properties associated with this eigenvalue problem are that the eigenfunctions corresponding to the eigenvalues, if we take two eigenvalues, lambda j and lambda k, that are not equal, so they are distinct eigenvalues, and we evaluate this integral with phi j inserted here. Phi j is the eigenfunction corresponding to lambda j, and phi k is the eigenfunction corresponding to lambda k. And we multiplied the product of these two functions with this weight function r, which you may recall is a positive function, that this integral over the interval 0 to 1 where the problem is defined is exactly equal to 0 when lambda j is not equal to lambda k. So for distinct eigenvalues, the corresponding eigenfunctions form an orthogonal set of functions. They are orthogonal, and we can think of this orthogonality in terms of an inner product being defined by this integral. So we can use the symbol small brackets around phi j and phi k, and we can say if we evaluate that integral is exactly equal to 0 when lambda j is not equal to lambda k. For distinct eigenvalues, the eigenfunctions are orthogonal. Furthermore, we can normalize the eigenfunctions. We can normalize them such that when j and k are the same, if j and k are the same, then this integral is actually equal to 1. And this is possible by rescaling the eigenfunctions themselves. Remember that we have a homogeneous boundary value problem, and so any constant times the function is also a solution to the differential equation and the boundary conditions. And so we can scale the function such that this integral is equal to exactly 1 when j is equal to k. And so this, as we saw before, they are orthogonal. When j and k are not equal, then we get 0. When they are equal, we can normalize them so that this is equal to 1. And so then we can use a shorthand for this using this notation delta jk, which is a Kronecker delta. And that symbol just abbreviates this form that we have written here, that when j is not equal to k, then we have 0. And when j is equal to k, we have equal to 1. So given this property, a very important consequence which makes this whole discussion very useful is that any square integrable smooth function f of x defined on the interval I, which satisfies the boundary conditions of the problem. What are the boundary conditions? The homogeneous boundary conditions on the Sturm Liouville problem that we had posed. So if the function satisfies these boundary conditions, this function can be expressed in terms of an eigenfunction expansion. It can be expanded in terms of these eigenfunctions, or this expansion we can also call a generalized Fourier series, just as a Fourier series is an expansion of some arbitrary square integrable function. This would be an expansion in terms of these eigenfunctions, not in terms of Fourier series or sines and cosines, but in terms of these special functions. So f of x can be expanded as a series with coefficients a sub j corresponding to the eigenfunction phi of j, j summed from 1, 2, 3 all the way up to infinity. And of course in practice it can be truncated at some value. This sum can be very useful in terms of approximating the function. And so the same thing can be said in another way. We can say that the set of functions phi j provide a complete basis for arbitrary functions f of x on I, which satisfy the boundary conditions and this integrability requirement. And so one way to demonstrate this is a simple algebra. We propose this and then work out the coefficients a sub j. And so this is a simple exercise which you can do. We can multiply both sides by phi k, where k is not equal to j, and integrate by multiplying with the weight r, and use the orthogonality property to derive this result that a sub j, the coefficient of this eigenfunction expansion, is simply given by this inner product between phi j and f. And remember, we had defined the symbol here, and I'm reminding you what this notation means. It means that take this function, put it here, take this function, put it here, multiply the product by this weight function r of x, which is a positive number, and integrate it over 0 to 1 and evaluate this number. And that number would be the value of aj.